minus a. So there's two ways to think about a difference quotient as the denominator of that quotient gets smaller and smaller. One way is to say, let x get closer and closer to a, then their difference will get closer and closer to 0. Or we say, take a number a and then move it over by a small number h. These two limits are computing the exact same thing, and if that limit exists, then we say the function is differentiable at the point a, and that limit we call f prime at a. So this derivative is what we'll be studying and using for the entire next couple of chapters of the text. The derivative measures the slope of the line which goes through the point a comma f of a and which is tangent to the graph of the function. The derivative also measures the instantaneous rate of change of the function at that point. This is very useful if the function is something which is changing over time, but also things which change relative to space can be used, the derivatives can be used. We also know that the derivative produces the best possible linear approximation to the function near that point. So many different perspectives on what the derivative can actually do for us. We have many ways to write the derivative because it was actually developed independently by two very important mathematicians. Isaac Newton was the first to come up with the idea of the derivative, although he didn't call it the derivative, he called it the fluxion. And so his is the name fluxion, which we don't actually use anymore. He also came up with this prime notation. So if we use f prime of x or y prime of x or just y prime to talk about the derivative of a function, then we're using Newtonian notation. Now Leibniz was the other mathematician who came up with the ideas for calculus. Actually only came up with it about 10 years after Newton did. But as you can see, his notation is entirely different. His intuition was also entirely different, and the way he expressed his derivatives was in terms of a fraction of infinitesimals. So he called it a dy, an infinitesimal number, and divided it by another infinitesimal number, dx, and the quotient was the derivative dy dx. So we can say dy dx, or d by dx of f of x, or just df dx. So Newton was the first person to come up with this. He uses the prime notation. Leibniz was the second, and the word derivative comes from Leibniz, and also the Leibnizian notation for the derivative. And they're linked by looking at the definition. The derivative of the function at the point x can be expressed in terms of this limit. The limit is delta x goes to 0 of f of x plus delta x minus f of x over delta x. What's changed from the previous times I put up the limit definition of the derivative? Well, I used to have an h here. Now I'm calling it delta x. And the numerator, f of x plus delta x minus f of x, is the change in the function values across a small change in the function inputs. So it's the change in the y values after you move x by a small amount delta x. So this difference quotient can also be written as delta y divided by delta x. It represents the slope of the secant line connecting 2 points on the graph of the function. The first point being x comma f of x, and the second point being x plus delta x comma f of x plus delta x. So delta y divided by delta x is an actual slope of an actual line, and in the limit it becomes the derivative. So what we have is a nice connection between the limit of a finite difference quotient and this infinitesimal. All right, Leibniz liked the idea of infinitesimals. We don't actually use infinitesimals because they don't represent actual real numbers. But it is quite useful to think of dy divided by dx as a quotient, even though we're not actually dividing any actual numbers. Some of the theorems about derivatives are more recognizable when we write them in Leibniz notation because Leibniz notation suggests them. So that's one reason that we like Leibniz notation. We took a few of the derivatives in the previous class, and let's take a look at how those went, and also what we can interpret from the derivative. So first function that we'll study is f of x is x squared, and in the last class we used the definition to find f prime of x. Here's how it went. Computing the derivative from the definition always amounts to writing down the limit of a difference quotient. In this case, we want the limit as h goes to 0, f of x plus h minus f of x divided by h. Now what is f of x? F of x in this case is the squaring function. So f of x is x squared. F of x plus h is x plus h squared. And this is the thing that we want to find the limit of as h goes to 0. Now whenever taking the limit of some algebraic expression, the first thing we should always try to check is, can we just plug it in? Can we just plug in h equals 0 in this quotient? And the answer is no, we can't, because the denominator is h, and if we plug in h equals 0, the denominator is 0, and we don't have a limit law for limits where the denominator is 0. Does it mean that the limit does not exist because the denominator goes to 0? Actually, no, that's not true either, because if you look at the numerator is also going to 0 as h goes to 0. Because as h goes to 0, the first term, x plus h squared, becomes x squared, and then we subtract from that x squared, so the numerator does go to 0. So this limit is of the indeterminate form 0 over 0, and in those situations anything can happen. What happens here? Well, we can find that by multiplying out the numerator and simplifying it. So when we take x plus h and square it, it becomes x squared plus 2 times x plus h squared. And I subtract from that the x squared, which is waiting for it right there. Now I've crossed out already the x squared and the minus x squared. You can see that these are going to cancel. So I can simplify my quotient as 2 times x times h plus h squared divided by h. And what I notice now is that every term is a multiple of h. I can cancel an h from each of the terms in the numerator, leaving 2 times x and then 1 extra h. And canceling the h from the denominator leaves a 1. So this quotient then reduces to just 2x plus h. And now what I see is not a quotient where the denominator goes to 0, but a simple polynomial, and there's no problem with just plugging in h equals 0 to a simple polynomial.